Did everyone get my email about the office hours? Okay. So I added one on Friday mornings and Wednesday mornings. Monday, Wednesday, Friday mornings, 9 to 10. I'll also be available on Thursdays and also on afternoons. But again, available. Just check with me before arriving outside of those hours. But mornings, I'm there. All right. So today we'll begin chapter 3, OpAmps. Operational amplifiers, or OpAmps for short, are created from something known as differential amplifiers using BJTs. Okay, so for a transistor, we saw how we can create an amplifier by adding a few more components, around it. And so an operational amplifier is a special type of an amplifier created using BJT differential amplifiers. Okay, so op amp. Special type of differential amplifier. To give you an idea, I'm going to draw a very simple circuit using two BJTs. And then I'll explain. So a differential amplifier, unlike a standard amplifier circuit, has two inputs versus one. In the BJT, the amplifiers that we saw, the common emitter CE amplifier, we had the input signal being applied to the base, right? The C amplifier, we had one single input. That input was being applied to the base of the transistor. In a differential amplifier, you have two transistors and you apply an input to the base of both. Thus, you now have two input amplifier. And the reason it's called a differential amplifier because it amplifies the difference between the two. Okay, this is a very simplistic connection that I've shown here, but this is just for illustration purposes on how we can create a differential amplifier. Okay, so again, the word differential comes from the fact that it amplifies the difference between the two inputs. And so an op amp is a special kind of differential amplifier. Okay, some of the properties of an op amp are listed here. We are not going to study the internal working or the internal circuitry of an op amp. Okay, we are only going to look at the op amp as a building block, meaning we take the op amp off the shelf. It's a chip, it's a microchip. You simply buy it off the shelf. You add a few components, external components to the op amp, and you can create whatever we want. Well, within the operation, of course. So you can create an amplifier using an op amp. You can create a filter. Remember passive filters in 201? So we can add the same components like capacitors and inductors to an op amp and create an active filter. Active filters meaning it can provide some gain, it can provide some amplification, and it can filter at the same time. Can use it for impedance isolation. We'll talk about that separately. And then the other, one of the most common examples would be in audio processing. We can use it for sensors, for comparing different voltage levels or different signal levels. And so we can use it as a comparator. In your lab kits, you should have both an op amp as well as a comparator. Yeah, so there are two 8-pin ICs or 8-pin chips in there. One of them is an 741, the other one's a comparator. So you can use the op amp as a comparator. And then also oscillators. Oscillators are for generating signals. So signal generators. So it's a very versatile device. Okay, it's a very versatile device. And again, we are not going to look at the internal circuitry of the op amp, not the internal workings. We're going to use the op amp as a building block and build our circuits. But it is worthwhile to take a look at the internals. So this is by far the most common op-amp, known as IC741, or simply 741. Okay, and this shows you the pinout. This is the pinout of the microchip. If you look at your lab kits, you will see a small you'll actually have two of these microchips. One of them is a 741. The other one is a 855. 855 is just a comparator. It's not an op-amp, but the 741 is an op-amp, and we can use that op-amp as a comparator. And this is the internal circuitry of the 741. This is one single semiconductor microchip. Okay, all of these components are built on the same piece of silicon. All the transistors, all the resistors, part of the same silicon die. And we can take this chip, add a few external components to it, and you can create multiple different applications. Okay, so we simply create this by adding external components. Okay, so the question people generally have, or students generally have, is how can we simply add external components and it works? Well, the reason is this: when we add external components, we are actually providing a connection between the two terminals, right? And so depending on what kind of connection we provide, the building block will change, or the internal circuitry will change. Okay, so let's look at what an op-amp looks like. So this here shows you the symbol of an op-amp. It is typically a triangle. I'm going to enlarge this here, and I'm going to show minus and minus plus. It is typically drawn as a triangle with the arrow pointing towards the right. The output is at the right, and the two inputs are on the left. The reason I'm drawing this out separately, even though I have it on the left, is because of the terminals. So we have two terminals. One of them is labeled as the inverting input. The other one is labeled as a non-inverting input. And those are represented with a plus and a minus sign respectively. On the left, the circuit diagram here in this figure, not the circuit diagram, so the symbol in the left has the non-inverting terminal at the top. Inverting is at the bottom. Typically, when you see op-amp circuits, it'll be shown like this: inverting at the top and non-inverting at the bottom. It will not be labeled. It will not be labeled. Okay. The minus and plus sign implies that these are the inverting and non-inverting terminals respectively. Okay. It will not be labeled. It will simply show you a plus and a minus sign. That's it. This is just for the AC input signal, or any kind of input. We can apply DC also. One other thing that's not shown here is the power supply. Remember, for our CE amplifiers, we applied VCC and we applied VBB, right? We applied two DC power supplies. So for an op-amp, the power supply is shown like this. Minus VEE. Okay. So this also is implied. The plus VCC and minus VEE comes from the fact that You apply the voltage to the collector, and the other end it would be the emitter. That's where the VCC and VEE comes from. Collector to collector voltage, emitter to emitter voltage. But those power supply terminals are also not always shown. Okay, they are implied. Those are the DC biasing voltages. Without those DC biasing voltages, the op amp's not going to work. Okay, so in the symbol that, I mean, right here, the op amp circuit is simply an open loop circuit. Two input voltages are shown, V in 1 and V in 2, sorry, V1 and V2. The power supply is not shown. So even if it's not shown, it might be stated somewhere in the question or the problem statement. So it's implied. Okay, let's take a look at what this means. AOL, America is online. The A here refers to the gain of the amplifier. How is the input being transferred to the output? AV would mean voltage gain. The OL stands for open loop. And the loop refers to any sort of feedback path that connects the output back to the input. If there is no path between the output to the input, it's said to be open loop. Okay, it's said to be open loop. So the property of an op amp is that the open loop gain is infinite. Is infinite, and it amplifies the difference between the two input signals, V in 1 and V in 2. Output to input. So it's two modes of operation. If V1 is equal to V2, both signals are being applied to the same, not the same signal is applied to both the terminals. And so we call that as the common mode. So V1 is equal to V2. In differential mode, it's V1 minus V2. Note that V1 and V2 is just notation. More importantly, this notes that it means non-inverting minus inverting. The differential mode means the non-inverting input minus the inverting input. And that difference will be amplified. The reason this is important in electronics is because of noise. Electrical noise is present everywhere. Electrical noise is basically any unwanted signal, right? If you have a Verizon cell phone, then an AT&T signal is noise. You don't want it going in there interfering, and vice versa. If you have an AT&T wireless signal, Verizon signal is noise. You don't want it going in there. So if you have a differential amplifier like this, any noise signal that's present in the surrounding, in the surroundings of the terminals will appear equally at both terminals. So if we can reduce that difference, not reduce the difference, sorry. If we can attenuate the common signal that appears at both terminals, we can completely reject any noise signal that comes at the terminals. And only the difference in signal is amplified. The common signal is rejected. And that's a very important property of these kind of circuits. Okay. So the properties of an open loop op amp or an ideal op amp is that it has infinite input impedance. It has zero output impedance, so it does not load the circuit. It has infinite gain for differential input and zero gain for common input, meaning it rejects noise signals, because noise signals would appear at both input terminals. And then it also has infinite bandwidth. Infinite bandwidth would mean that the frequency characteristics would be flat. In real life, though, they will start to roll off. As the frequency increases, the output will start decreasing. Okay. Ideal op-amp, it remains a flat line. So the equivalent circuit of an op-amp can be drawn like this. You have two inputs, V1 and V2. The differential input VID is V1 minus V2. The ID stands for differential input. So and V out can be described as a dependent voltage source, a dependent voltage source that is dependent on VID. So the gain times VID. As VID increases, V out also increases. Okay. All right. And a couple of concepts that I want to go over before we end for today. So we can model the infinite input impedance as Z in between the input terminals. Okay. Z in tends to infinity. And the output, V out minus A times V2 minus V1. If you note, V1 represents the input terminal, V2 represents the non-inverting. What does the minus sign indicate? It's flipped. It's 180, or it's inverted. It's 180 degrees out of phase. So the inverting input simply means that the output will be 180 degrees out of phase with the input. If you apply a signal, a small sine wave at the inverting terminal, then the output would be amplified and inverted. If you apply the same signal to the non-inverting terminal, then the output would be amplified but not inverted. That's all it means between inverting and non-inverting. Okay. So the minus sign simply indicates output is 180 degrees out of phase. But let's come back to Z in. If Z in is infinity, that means that current flowing through Z in is 0. If current is 0, what is the voltage across Z in? What is the voltage between these 2 points? Anyone? I heard someone. It should be 0. Current is 0. So the voltage is also 0. In any circuit, when is a voltage considered to be 0? When both points are the same potential. And if you recall, what do we replace a voltage source when we reduce it to 0? A short. So if voltage is 0, we can say a short exists between the 2 terminals. So here's the concept. Because Z in tends towards infinity, we say the input impedance is infinite, we can say there is a virtual open connection between the 2, meaning the 2 terminals are virtually open. However, at the same time, we can also say there is a virtual short that exists between the 2 terminals. And depending on our analysis, it's convenient for us to choose either a virtual open or a virtual short between those 2 terminals. This is virtually short-circuited. Hence a virtual short. It's a very confusing point. And at the same time, we can also say it's virtually open because Z in is infinity. In reality, there is some sort of current that goes through. Yes, go ahead.
Yeah, could you elaborate on what virtual short actually means? Like, what do you mean by virtual?
So virtual short, in this case, we would simply say the voltage at both terminals is exactly the same. And because the voltage is exactly the same, we say that they are virtually short-circuited. It's not, there is no short circuit, there's no wire that is actually physically present between the 2. But because the voltage at both terminals is supposed to be the same, we say they are virtually connected by a wire. So that concept is referred to as a virtual short.
Thank you.
Mm-hmm. And to take that further, if one terminal of the 2 is grounded, then the other one is set to be connected to virtual ground. And so that's the concept of virtual ground. It comes from virtual short. So it's not really a short and it's not really a ground. So we say it's virtual ground, virtual short, and virtual ground. Not real. And again, that's for the purposes of analysis. So we'll use this concept to analyze different kinds of amplifier circuit using the OpAmps. All right, so we'll end class here today. We'll pick up here again on Wednesday.